oscillation reaction. So we have boiled starch and hydrogen peroxide, and we're going to add malonic acid, manganese sulfate, potassium iodate, and sulfuric acid. You ready, guys?
Yeah.
Okay, ready? Hold it up, come. Tip and pour. Pour.
So
Sure, it's all of it.
If they're blue.
Oh, well, so as you see, we're going through stages of 3 stages of iodine and starch solution. When the iodine goes all the way to the reduced form, it goes to a iodine starch solution. Then it becomes fully oxidized back to iodate. And it goes to where it's clear, and it goes into iodine, where it's turning yellow, but when it builds up, it reforms as starch.
Daddy, why do we need to crack it?
The glasses is an important part of safety. If you were to spill things onto yourself, you need to protect yourself.
Like we got to be putting on the ice. Yeah.
Mm-hmm.
We don't really need gas right now.
Well, let's stand back a little bit further then. So see, do you think this is going to keep going forever? Or do you think it's going to stop at some point?
I think it'll. I think it'll stop at some.
What did we just notice there?
It seems into another color.
Well, no, but it seems to be taking longer and longer to change into another color. This is also showing some kinetics, meaning the speed.
It'll stop soon.
So what did we actually observe? We saw that the iodate undergoes several transformations between colorless iodate and iodide, converting to yellow amber iodine, and then in the presence of iodide it combines to form the I3 minus, which is stabilized by starch, which is then can be slowly removed and converted back to the iodide and iodate again. We know what happens when we mix all the components together. We get that beautiful oscillation reaction. Know the colors are caused by the iodate and the starch. We know that the hydrogen peroxide is our oxidant that helps us undergo these changes, and sulfuric acid is our catalyst.
What is the purpose of the manganese and of the malonic acid? We're going to try to look at that. So this is, I'm taking out the malonic acid. And this is just manganese. I'm adding to here. Now I'm going to quickly add, this is the peroxide. See what we can see. Without the malonic acid, it's just forming yellow, and it's doesn't seem to be changing. So what is that yellow? That yellow is the iodine. So now there is some reverse reactions that should be occurring. Well. Getting it to dark. Now this could be, the slowness of this reaction could be due to the fact that the peroxide was chilled. So we'll try that again at the end and see if we can see anything different. But let's see. So it's eventually, so we saw a large iodine buildup, and now it's formed the I3 starch complex, and it doesn't seem to be changing. I'll look back at this in a few seconds, but I don't think it's going to change anymore. So despite all the peroxide and all that, you're seeing almost irreversible buildup in the I3 starch complex.
This solution will simply be lacking the manganese. It will contain the malonic acid instead.
Now our peroxide. So, no manganese. Or no manganese or very little manganese. Assuming I didn't screw this up. Stirring. And we see very little color change.
So it appears there is no reaction, or at least no observable reaction. The manganese proves to be a crucial component to allowing this reaction to go forward. Very interesting. Now to mix
the solution without malonic acid to the solution with no manganese. So mixing them together, see what is going to happen. Here we go. As you see, it cleared out, reformed amber, and that's now begun to oscillate. Very slow at start. So that manganese is there to help ease the oxidation, but the malonic acid is there to help remove your iodine starch complex and get us back to the starting point again. So without those, we will see absolutely no oscillation.
The initial reaction is iodate reacts with hydrogen peroxide to form a peroxyiodide. Now, if this was allowed to build up, we wouldn't need that manganese. Once the hydrogen peroxyiodide forms, it can further react with iodate to form a peroxyiodide radical, which is then reduced by manganese to reform hydrogen peroxyiodide. This allows this to build up so that we can form a new compound, a hydroxyiodide. This results in the net reaction of either iodate goes to hydroxyiodide, or that the peroxyiodide goes to the hydroxyiodide. Either way, the result is the same. All that has happened before even a single color change has occurred. So without that manganese, we couldn't really form up enough peroxyiodide to generate a color change. So now this hydroxyiodide can react with hydrogen peroxide to form some iodide. Now this iodide is the key component that we need. Once we start forming that iodide, it can either react with some iodate to form more hydroxyiodide and peroxyiodide, or the iodide can react with peroxyiodide to form a lot more hydroxyiodide, allowing that to build up. Finally, this hydroxyiodide can react with regular iodine ions to form our iodine, which is our first real color change. And as this is formed, it can further react with more iodide to form our I3 complex. But as this builds up, the malonic acid can break it down again, and this causes the change back to colorless. as we have to reform more iodide, more iodine, and more I3. This is why the purple beaker took so long to change back to colorless when I mixed in the malonic acid. We've had a long time to build up a large quantity of the I3 complex.
Hopefully you found this interesting and informative. I hope to present more experiments for you to learn about in the near future. Please like and subscribe and comment and tell me what experiments you'd like to see. I'll see what I can do based on what we have available in the lab.